Hello everyone and welcome back to the OpenGL 3D game tutorial series. In this fourth episode we see how to create the shaders in OpenGL. In particular we will see how to create and use shaders in order to define the way in which polygons are rendered on the screen. As always we will face three main parts: requirements, design and implementation of all the necessary things to create and use the shaders. Let's start with the requirements. We need C++ IDE. In this series we use Visual Studio on Windows and Qt Creator on macOS and Linux. The target platforms are Windows, macOS and Linux. The target graphics API is OpenGL, and last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. What's the problem to solve today? We want to create and use the shaders in OpenGL, so we should add a shader class inside our class diagram, and since a shader is a graphics resource, the graphics engine class should be in charge to create this class with a suitable method like createShader. But before to continue the design of the class diagram, we should deepen what are shaders and why we should use them. A shader is nothing more than a little program written in a specific language called GLSL that is executed by the GPU. Its main purpose is to allow the developer to define the way in which a polygon is rendered on the screen. We have different types of shaders. The main ones are the vertex shader that, as the name suggests, allows to transform the vertices provided by the vertex array object. The fragment shader that instead allows to define the way in which to color the pixels of the surface of the polygons we want to draw. In other words, the shaders allow to customize the execution of the graphics pipeline. As we have seen in the previous tutorial, the graphics pipeline is a series of steps executed when a draw function is called, for which the raw 3D vertices retrieved from the VAO are transformed to 2D pixels rendered on the screen. In particular, when vertex processing step is executed, the main function of vertex shader is called, and the code written in the main function determines how the vertices are transformed. The same thing for the fragment shader step, where the main function of the fragment shader is called to define the color of the pixels. This is an high-level explanation about shaders. Let's see in detail how we can effectively create and use these types of shaders in OpenGL. We have to create the so-called program object with the glCreateProgram function. This object acts as container for all the types of shader we want to use for the rendering of a specific polygon. Then we have to create and compile the various types of shader with the following functions: glCreateShader, glShaderSource, and glCompileShader. And in the end we have to add or attach each of these shaders to the program object with glAttachShader function. Once all the shaders we want to use have been attached, we have to finalize everything with the glLinkProgram function. Very well, now that we have all the necessary information, we can focus again on the class diagram. At this point we could call the OShader class OShaderProgram, and we can add two important methods like attach and link. The attach method should allow us to compile and attach the shader file passed as parameter to the shader program. The link method instead should allow us to finalize the shader program object. If you have questions, doubts or comments about this topic, don't hesitate to leave them in the comment section of this video or in the Discord server. The link to the Discord server is available in the video description. Also, if you find these tutorials helpful, please consider to support their development on Patreon. Every single contribution makes the difference, regardless the amount. Very well, we have gathered all the necessary information to start the implementation. Let's start by creating the shader program class. Let's include the header file as usual. Now we can start to add the constructor and destructor methods. Let's include as usual the glad header file. The first thing to do as soon as we create a shader program object is to call the glCreateProgram function that returns an ID. Let's store it in a suitable attribute that we can call program ID. The next thing to do is to pass the various shader file paths when we create the shader program. In order to do that, let's go to all prerequisites header file and let's create a structure called OShaderProgram.desc. In this structure, let's place the vertex shader file path and fragment shader file path. Good, let's use it in the shader program constructor. Now that we have this data, we can start to add the attach method, for which we can create and compile any kind of shaders. Let's add as parameters shader file path. Here, we should add a parameter that specifies the type of the shader we want to create and compile. For this purpose, let's go to all prerequisites header file and let's add an enumerator called OShaderType. Here, let's add vertex shader type and let's assign to it the 0 value. And at the end, let's add the fragment shader type. Very well, let's use it in the attach method. At this point, let's implement it. Before to go further, let's code GL delete program in the destructor in such a way to deallocate the program created during the constructor. The first thing to do here is to open the shader file. So let's include the fstring header file and let's create the input file stream object. During the construction of fstream object, we have to pass the file path. In order to check if everything has gone well, let's call the isOpen method. If the file is open, then we can go further, otherwise we should exit. In order to extract the entire content of the file, let's include the sstring header file and let's create a string stream object. In this object, let's reverse the entire content of the file by calling the rdbuff method of ifstream. At this point, the entire source code of the shader is stored in the string stream. In order to pass this code to the OpenGL function, we have to pass it again to a string object. Let's call it shader code. Once we have finished, let's close the file. Now let's call the glCreateShader and let's create a vertex or fragment shader based on the type passed as parameter. And of course, let's store the shader ID. At this point, we have to call the glShader source to which we pass the source code of our shader stored in the string object. Once the shader code is ready, we can compile it with glCompileShader. Now we should check for eventual compile errors. We will do that in few moments. For now, let's move on and let's attach the shader file just created to the program object with GL attach shader. At this point, we should release all the shaders created during the destruction. For that, we should store all the IDs of the attached shader in a suitable array. So let's add this array as an attribute and let's call it attached shaders. With a size of 2 unsigned integer elements, the IDs of the vertex and fragment shaders. Very well. At this point we can effectively release all the shaders with GL detach shader and GL delete shader. The last thing to do is to call attach in the constructor in order to compile the vertex and fragment shaders. And in the end, let's create and call the link method to finalize the program object. Very well, the shader program class is ready. Let's go ahead and let's define a shared pointer for the shader program class. Let's call it, as usual, shader program PTR. Let's go to our graphics engine class and let's add the method createShaderProgram. Here we should create this resource in the same way we had done previously with the vertex array object. As last thing, let's add the setShaderProgram method and here we should use the GLUseProgram function that requires the ID of the program created in the ShaderProgram object. In order to get this ID, let's add a suitable method in the ShaderProgram and let's call it getID. So far so good. Now that the shader program in general is ready, we can go to the OGame class and we can start to create our shader program in the onCreate method. Let's store it in a suitable attribute. At this point we can use it in the onUpdate method by calling the setShaderProgram method. What next? We have to create the shader files. Let's create them in a suitable folder called Assets. For the moment, let's place it in the project folder, and then in the Assets folder, let's create a further folder called Shaders. And here, let's finally create the vertex shader file. In order to identify the type of shader, let's give it an extension like .vert. Let's do the same thing for the fragment shader by giving an extension like .frag. So far so good. It's arrived the time to write the code of our shaders. In the vertex shader, let's start by adding version 4.10 core. This tells to the shader compiler what type of features set we want to use. Since we cannot use versions of OpenGL greater than the 4.1 because of macOS, let's use the feature set of the 4.10 version. Then we can start to add the main function that is really similar to what we do when we create a C or C++ program. A vertex shader, as we have seen in the introduction, takes the vertices from the VAO and transforms them in this main function. But where do we have to pass the final transform vertex? To a special object called GLPosition, that is the main output of the vertex shader. Very well, the problem now is that we have to find a way to get the vertices from the VAO. We can do this by writing the line layout brackets location equals 0. The 0 is the index of the attribute we want to retrieve the data from. We have defined it in the vertex array object constructor with the GLVertex attribute pointer. Then we have to write the in token in order to declare that this is an input attribute, and as last thing, let's define the type of this attribute, that is a vector of 3 elements, and so vec3. And finally, let's call this attribute position. Now we can pass it to the output object. For now we don't transform it since the vertices we have stored in the VAO are already transformed in screen space. Good, let's start to write the fragment shader, and since it's nearly identical to the vertex shader, let's copy-paste it. The only difference here is that in the fragment shader we have to define the output in the same way we have defined the input attribute in the vertex shader, and since the output of a fragment shader is a color that in general is composed by 4 elements that are the red, green, blue and alpha channels, let's use a vector of 4 elements, and so the vec4. In the end, let's pass a fixed color to the output attribute, in this case a green color. The only thing that remains to do is to pass the shader file paths as parameter to the create shader program. Let's see if it works, and it works. Let's make some tests by changing the green color to blue color. And then let's test the vertex shader by translating to the right the top vertex of the triangle. Very well, it seems to work. Now, in order to test further the shader, let's color each vertex of triangle with a different color. In order to do that, we have to add a further attribute in the VAO. This can be done by extending the OVertexBuffer data that we rename in OVertexBuffer with a list of attributes. In this way, the user is able to define an arbitrary number of attributes. So let's define a OVertex attribute structure where we add a number of elements attribute. This attribute will determine the usage of vec2, vec3 or vec4 in the shader code. Then let's add in OVertexBuffer a pointer to an array of vertex attributes. Let's also define the number of attributes of this array. At this point, let's rename all the references to OVertexBufferData to OVertexBufferDesk. Once we have finished, we can use the attributes just defined in the OVertexArray object in order to declare multiple attributes. So let's create a for loop and in the GL vertex attribute pointer, let's set the index attribute with the I variable, the number of elements with num elements, and as last thing, let's pass to the last parameter the offset in bytes from the previous attribute. So, if the I variable is 0, we don't have any previous attribute, so let's pass 0. Otherwise, let's pass the number of elements of the previous attribute multiplied by the size of float. In the end, let's enable this specific attribute with the I variable. That's all. One last thing to do is to add the colors to the vertices list. We have to define an attributes list with two attributes composed by three float elements. That correspond respectively to the position and color attributes. In the end, let's pass the attributes list and its size in the createVertexArray object method. At this point, we have to get the color data from the vertex shader by defining a new attribute in the same way we had done for the position, with the difference that now the index is 1 and not more 0. we have to define an output attribute that allows us to pass the color data from the vertex to the fragment shader. And as last thing, let's go to the fragment shader and let's define the input color attribute related to the output color attribute of the vertex shader. At this point, we have only to pass this color retrieved from the input to the output color. And let's remember to change the size in bytes of the new vertex, that is the composition of the three elements of the position with the three elements of the color. And it works! Let's change a bit the background color. And let's remove the vertex translation. Very well. The graphics part is ready. Now we should focus on the error handling of the shader program class and other classes. Let's go to our prerequisites header file and let's define three macros. OGL 3D error, OGL 3D warning, and OGL 3D info. In OGL 3D error, we should throw a runtime error exception with a particular message that we can pass as parameter in the macro. To better handle the message, let's use the string stream object. This object allows us to concatenate easily any type of variable from strings to number and convert them in a final string. Very well, let's go ahead and let's define the OGL 3D warning macro. With warning macro, we want only to inform the user that a particular event requires its attention. To do that, we can use the so-called clog, that stands for console log, that is similar to cout, but it is designed specifically to handle logging messages. In this case, we use the wide char variant of clog in such a way we can use Unicode strings. Good, let's do the same thing for OGL 3D info. At this point, let's start to use these macros in the vertex array object. Here, during the construction, we should check some parameters, like list size, vertices list, and vertex size. If one of them is null, we should throw a runtime error. Let's do the same thing even in graphics engine, in particular when we initialize the GLAD library. At this point, we can start to handle the errors during the creation of shaders, in particular when we open the file and the file is not correctly opened. In that case, let's send a warning message to the console in order to inform the user that a specific file has not been found. Now, let's check if there are errors during the compiling of shaders. Let's use the glgetShaderIV to return a specific value, in this case the length of the log message. If the length is 0, there is nothing to print. Otherwise, we have to call the glGetShaderInfo log to retrieve the log message that can contain warning and/or errors. Also, we should inform the user when the shader has been compiled successfully. In this case, let's use the OGL3D info macro. Cool, let's copy paste the check for errors done here in the link method. Let's see if it works. And it works. The program informs us that the shaders have been compiled successfully. Let's make some tests and let's put some errors in the vertex shader. As expected, the program informs us that the basic shader.vert contains errors. That's all for now, folks. Today we have seen how to make vertex and fragment shaders and how to handle basically the errors. The next time we will see how to use uniform buffer object to make animations. I hope you enjoyed this video. See you soon. Thanks for watching.